forward this. Okay, so we just looked at what happens if you have some charge here and another charge here, 10 centimeters away. Then the force attracting this charge to this one is 20 newtons. Then when we move out to 13 centimeters, which becomes less, the force is about 12 newtons. Then we went out another 3 centimeters, saw that we'd have 16 over 10 squared, which gave us about 1/4 of the original force. Okay? 5 newtons. Is that right? Yeah. Okay. Something wrong with that 1/4. Anyhow, not worried about that. You could work that out. 3 centimeter increment by 3 centimeter increment, right? Well, what you're doing then, when I first asked how much work does it take to get from here to here, the answer I got was, well, 20 newtons times 3 centimeters. Then I asked, is that an overestimate or an underestimate? Somebody said, well, it's an underestimate because when you move this way in an orbit and then that way, you get less. Well, actually, by conservation, you get, by the conservative force, you get the same thing. But there's still an intuition that goes along with orbital mechanics that could be related to this. And the intuition just goes with the fact that 1/r² is a curve that looks like this. So if you do a straight line approximation between 2 points in that curve, you're going to overestimate it. Okay. Now here, you're overestimating it because the force falls off. Force is never 20 newtons after you start moving out. Okay. It does fall to 12 newtons. Then the question is, what do you use for your average force? You say, well, it would make a certain amount of sense to average the 10 newtons and the 12 newtons. The 20 newtons and the 12 newtons get 16 newtons and use that. Yeah, that would be pretty close. Still an overestimate, but not a terrible one. Okay. Now, all that is a predictor-corrector Euler equation, Euler approximation, which you ought to review in terms of this example. Because when you saw it, it was a bunch of symbols. That can be difficult to unpack when you first see it. And if all you're thinking about is the symbols, then you're not going to have the very, very simple understanding of what it does. It's very simple. If we take the force here and use it for the whole 3 centimeters, we get a result. If we average these two forces, that's a predictor corrector. We predict what is going to be out here and correct by the middle and stuff like that. And it's not exactly predictor corrector because that's what you use to solve a differential equation, but it's very much the same idea. Well, go on from there. Okay, now what we're really doing though is building up an integral. Somebody observed that fairly early when we were starting to talk about it. So now you got a force of 20 newtons when R equals 10 centimeters. You write the proportionality. If you know Coulomb's law, because that's what we're talking about here, these are charges. If you know Coulomb's law, you know force is an inverse square force. And somebody mentioned that very early when we said these are charges. Oh, it's an inverse square force. Okay. Didn't necessarily always get applied, but it often did. Okay. Force is proportional to 1/r². And since we know the force at a given distance, we can find out what our proportionality constant is. Force proportional to 1/r² means the force is a constant over r². Often we use K for the constant, but since we use K for the Coulomb constant. 9 times 10 to the 9th Newton meter squared per Coulomb squared. Don't use K here because that'd be real confusing. So we do this. So what's our constant? Well, we know the force is 20 newtons when R is 10 centimeters. So we immediately find that the constant is 2,000 Newton centimeters squared, which is about 2/10 of a Newton meter squared, because a square meter is 10,000 square centimeters. Think it's 100 square centimeters. Just take 100 little 1 centimeter squares and try to build a square meter out of it. You find that you need 100 of hundreds. Okay. And there are other ways you understand it, just by proportionality again. Okay, well, so we got this rule for the force. Then between R sub I and R sub I plus 1, like maybe R sub I is 10 centimeters, R sub I plus 1 is 15 centimeters or 13 centimeters. The force goes from this to this. In this case, it would be from 20 newtons to 12 newtons, roughly. Okay. If Ri minus 1 minus Ri, that is a distance from here to here, is small, like if we were going by 3 millimeter increments, you could just randomly pick any point between 10 and 10.3 centimeters, calculate the force, and you would be off by only a small amount. And if you keep doing that, and then if you let that increment shrink to 0, your error shrinks to 0. That's how you take a Riemann sum and let it approach an integral. Something that typical students in science, engineering, STEM type fields don't really grasp completely until somewhere in their second year of calculus and physics. Okay? So you want to start grasping that because you're getting close to the end of your second year. Okay? So you really want to know that. You really want to understand how it work and some of the technical aspects. Engineers often ignore some of the details of the mathematical development, but remain aware so they could reconstruct them if they need them. Often you don't need them, but I wouldn't recommend forgetting it. And ask your engineering instructor if that's accurate. Because he's in the field, I'm not. Okay. Anyhow, this does lead to the question. The question is, how much energy do I need to separate this thing to the next wall over there, which is infinity as far as this thing's concerned? Okay. And work is going to be the integral from 10 centimeters to infinity of F over R squared R. Okay. Which is going to be negative integral from 10 centimeters to infinity of, okay, now I've got to get my directions straight here and I'm being careless. The force is this reaction. You're moving in that direction, right? So let's make sure this is the magnitude of the force. And to be accurate, since we have opposite charges, it's going to be a negative constant. So it's going to be the negative of this. So now we're integrating the negative of 2,000 Newton centimeters over R squared dr from 10 centimeters to infinity. This is equal and opposite to the work done by the conservative force that's pulling these things together. So it's going to be the negative of the negative, and you can worry about that. But let's look at the integral. The integral is going to be 2,000 Newton centimeters squared over R. And negative negative makes us positive with the reciprocal R squared has an antiderivative is negative 1 over R. Now, this would actually be the limit as R goes to infinity. So it'd be like your integral would really be the integral from 10 centimeters to big R. Limit as big R goes to infinity. That's what a mathematician is going to tell you. And that's what's right, and that's what an engineer ought to keep in mind. But you know, if your variable's in the denominator and it's going to infinity, it's going to approach zero. You're just shortcutting this, okay? It's not a good idea to shortcut it without thinking about the fact that it's really a limit. You get yourself in trouble sometimes, but you can often survive that, okay? So this ends up being minus 200 Newton centimeters squared, which is minus 0.02 joules, unless I'm doing something ignorant. Because a centimeter squared is a 10,000th of a meter squared. Take a 10,200, you get 0.02. Getting a confused gesture out there, which means I probably did something boneheaded. Yeah, talk about the other things right. Something didn't feel right. That felt a little too small. And it's not Newton centimeters squared. You got a centimeter in the denominator. Okay. There we go. All right. So be careful with units. I pretended to make that mistake just so somebody could catch me. Yeah, I know. It's funny. Um, all right. Well, potential energy of the system is negative 2 joules. This means in free space, if you released that particle from a very great distance, it would have 2 joules of energy, kinetic energy, by the time it got there. Okay? Does that make sense? So this system has a negative potential energy. If you release it, it's not going to fly apart. You're not going to gain kinetic energy. And I'm saying that wrong. Okay. If you move it closer, it's going to have maybe negative 4 joules. Okay. There's some point at which would have negative 4 joules. So its potential energy would have decreased. So it will gain kinetic energy as it gets closer. Does that make sense? Is what I said a minute ago, didn't it? Okay. Well, that takes a little bit of sorting out, and you want to get used to that. And the introductory problem sets attempt to do that job for you. I'm not sure if you've gotten to the part that does, but I think you probably have. Um, so you really want to have mastery of that. PE charges is equal, and that stuff that was written here that didn't show up still isn't showing up, and the stuff over there isn't showing up. It is starting to show up. Okay, I think all this is still visible, but this stuff wasn't. So this is my comment on limit as R goes to infinity, and that's what's really going on here. And you should sort that out. Potential energy of the system of charges. Should we say this right? In this case, we found the energy I've got a sign wrong here. Getting the work done by the force that would separate these objects, okay? And when I did this, I put a negative here, which is wrong because I have a negative sign on this integral. The 10 centimeters is your lower limit. Is upper limit minus lower limit. It's the value as r approaches infinity, which is 0 minus what you have here. So it's going to be positive. And what this is to separate the particles, okay? That's the work done against the conservative force, okay? And going from infinity to 10 centimeters, the conservative force would do positive work, okay? Because in moving from 10 centimeters to infinity, we would have to do negative positive work on the charge, which is equal and opposite to the work the field would do on the charge. Negative 2 joules is the potential energy of the two-charge system. And what's our definition of potential energy? Change in potential energy. Equal and opposite to the work done by the system. From your reference point to the given point. The reference point infinite separation. So if we consider these particles to be infinitely separated, and just take the furthest wall of the room to be infinity because the integral from there to infinity is minuscule. Okay. Then the electrostatic forces would do positive work pulling them in. Okay. Change of potential energy is equal and opposite to the work done by the conservative force. We don't have to think about the force we exert, but we can. The force we would have to exert to separate them is equal and opposite to the force that the field would do in pulling them together. So you want to sort that out. Now we have just a representation on the tabletop where you've estimated positions and stuff of 5 charges and a central charge. Okay, big charge and 5 small charges. How would you calculate the potential energy of that system? Well, just do the same calculation for every charge. You just integrate from the distance of that charge to infinity. Okay. Now, this does involve something that you've seen in multivariable calculus or are going to see probably even tomorrow. Okay. The definition of a conservative field. Okay. And once you have that, it helps pull all this stuff together. The result is you can just calculate the energy of each charge relative to that central charge and add them all up. So you could actually estimate at 10 centimeters, you got like 2 joules, right? What would you have at 20 centimeters? Well, it helps to have the general formula, so let me get that for you. It's just the integral. You could consider a straight line, separation R to separation infinity. Okay. Now, it doesn't have to be a straight line. It could be any old path to infinity because the fundamental theorem that we're going to look that's a very interesting thing. Since y'all have apparently been studying some orbital stuff and dynamics, am I right? Or yeah, okay. Read an interesting thing last night in this science fiction book that's been written by this guy who was a physics major, okay, and really smart. Coming up with some really neat stuff. Lagrange points. You know about Lagrange points? Okay. Yeah. The moon is blown up. In 24 months, the Earth is going to become uninhabitable. I think I talked about a little bit about that last time, didn't I? of the particles of the moon keep hitting each other. So the moon material keeps spreading out until it starts to impact the atmosphere. And all the energy there, it's going to turn the sky white, turn the surface of the Earth to 10,000 degrees and kill everybody. They've got a space shuttle up there. Now they're shoving everything they can up to the space shuttle and doing a bunch of stuff to try to escape. And this guy is wanting to go from the orbit of the space shuttle out to catch a comet that's in an orbit similar to the Earth's orbit. So he goes out to Lagrange point, where you can change from an orbit that's out of the ecliptic to an orbit that's in the ecliptic, so we can go meet the comet, put a nuke on it, and make it come back. Okay, very interesting. I mean, and the guy does a really neat job of making that tangible. Okay, well, digression aside, you got this, okay? And that's it. Right there is your potential energy function, and that saves you from having to do all the integration, although you should know how it's derived. Now, in fact, you better know how it's derived. I'm probably going to ask you to tell. It's a little better than 2/3. Okay, so it's worth making sure you can explain this. And it's that simple, except you got to be careful about your signs and your directions. Okay. Um, so, verify that. Make sure my sign is correct, think it through. If they're positive charges, then you have to do negative work to get them apart, which means it does positive work to pull them together. Does that mean you have positive potential energy? Well, think about it. If you go closer, you got to do work to get closer, which means you got to do work against the conservative force to get closer, which means potential energy is going to increase as you get closer. What's going to go to a lesser negative? So I think what I just said is right. But I'm capable of getting that backwards. So you want to think through that. Okay. I didn't know where we were going tonight, so I didn't think through it earlier. And I never trust myself to think through that. There are too many negatives and negatives. But if you want me to, I'll explain it carefully next time. The other thing I want you to think about is you got a situation like this. You got a charge big Q here, then you got a Q1 out here, and a Q2 out here, and a Q3 out here, and a Q4 out here, and a Q5 maybe here. You got arrows indicating magnitudes of these forces. Your arrows are probably not real accurate as far as their relative length. And I got a question here. The thing I was going to say here, and I'll append something in the end where I get the signs right. Okay, because I always screw this up. Thing I was going to say now, you got these forces. Now let's take the charge that's closest, which might be this one, and give it this much force. We're assuming all these charges are opposite in sign to this central charge. Then this one's going to have a force of almost the same, it's a little further away. This one's far enough away that maybe you get half the force. This one, a little closer than that. This one's the one that's closest. So anyhow, your forces are going to look something like this. This one should probably be bigger, and these rest of these should be a little smaller or whatever. Okay. And I've asked you to estimate what those forces would be and to estimate the components. So you could then do all kinds of trigonometry and everything, and that would be okay. But right now, we just want to be able to visually estimate these. Okay. So that you have the ability to believe your trigonometry. Then you go to the trigonometry, which is simple. Okay. But my next question is, what if these charges are exerting forces on each other, which they are? Okay. If these charges are not totally insignificant compared to this one, then if you want the potential energy of the system, you'd better talk about potential energy that brings this charge close to this one and this charge close to this one. Every possible pair of charges is going to have a potential energy. Okay. So it's just an illustration of how handy this can be. Okay. I mean, it's your potential energy function. U equals, okay, for every pair, okay, Q1, Q2 over R1, 2 squared, there's no vector, so you don't have to worry about the direction. And is this negative? Question mark on that. I'll work it out real carefully, and it'll be at the end of the video, okay? Because y'all have had a dynamics test. They've been harassing me over this for an hour. Okay, you deserve to let your brain go a little bit slack for up to 15 minutes.